Is scoring in football actually Poisson process? Our answer is no. In this video, we are going to learn some common lessons, recall what Poisson process, or simpler, Poisson distribution is, find out why Poisson process or Poisson distribution or whatever is not appropriate for football, is not too appropriate for football. We will find something more appropriate, still not perfect. And we even play a football game using candies. My name is Evgen Bashovy. You're watching Beta 5 AI. You are a peaceful person. But one day you assume, why would Russia invade Ukraine? It sounds like madness, so there must be a reason for it. And obviously you want to find reason for it. And there are, because Russia produces them a lot. And you read them, you change your mind, reads again, change your mind again, and then one day you find yourself writing something like kill them all in Facebook. Kill them all, those Ukrainians or what. Imagine how your peaceful state turned into kill them all. Yeah? It was all because of bad assumption that it is madness, that it does not make sense. Okay, I'm going to give you more sense. It is not very perfect, but still it is better than nothing. It is not a madness, but imagine, model this situation as a relationship between ex-husband and ex-wife. They had a divorce that was a peaceful one, but husband still thinks in the back of his mind that the ex-wife is his property. And then he comes and says, hey, wife, let's live together. Wife says no. Then husband says, okay, I'm going to kill you then. And your neighbors say, our moral support is totally with you, ex-wife, but ex-husband got guns. And frankly speaking, it's good to make business with him. So we are in this situation. At this very moment, as an ex-wife, you become a enlightened person in an instant. You start understanding that all victims in the world are connected with you. So there is a connection between you and victims of hunger or wars in Africa, in Middle East, in Asia, wherever on the in the earth. So, yeah, you are now basically Buddha. What you need to do now is a technical thing: survive. Help us survive. Links are there in description. Also, let us continue making good lessons for you to not make bad assumptions, for instance. Links are there in description. Okay, let's go straight to example of bad assumption. Okay, assume that you remember, first bad assumption, assume that you remember school geometry, right? It is already a bold bad assumption, but okay, there is a right triangle, the black one, yeah? And there is a blue line which dissects this angle in halves, yeah? And there is an height reconstructed from this line, and this height dissects this side in halves. All right. Assume that they intersect in this square in that point. Okay, good. Nice assumption, right? What can go wrong? Okay, let's do some more things, and let's make some lines. It is all made in Paint, in Microsoft Paint. So So it is height on this side, it is height on this side. There are lines connecting this point of intersection and these things of the triangle. And then slowly but surely you will find out that this part, so coming from this point to this point, equals to this part, because angles, you know, and this both are right triangles, and also these parts are same, because you know there are two parts, this and this and this and this, all are equal, so you get equality of these parts. It is now at this at this page now there is no trick. It is geometrical proof. Yeah, and now you will come to the good conclusion that this side, this one, has same length as this side in right triangle, you know. We didn't speak about these angles, about shape of this right triangle. We only said that it is right triangle. And already there are two sides of it are equal. Nice. Go and use outcome. Go and use results of that assumption. What was wrong? What was wrong here? The very first assumption. This line, which dissects the angle, always lands on this side between it. So between this point here and between this point here. So intersection of these lines must come somewhere outside of the triangle, not inside. Still, it was looking very good, right? It was looking very good, sensible, good assumption, leading to bad results. What can also bad assumptions do? Bad assumptions or incorrect assumptions lead us to random results. We don't know where they lead us. We only know that correct assumptions, if they do it with correct way, then they lead us to correct results. Everything else is kind of random. So if way of proving or if assumption itself was incorrect, then results are random. Random results mean bad expertise. Bad expertise including some underestimations and overestimations. And in terms of betting, bad expertise and overestimations mean losses. The more overestimation you made, it affects your decision-making process. You will apply somewhere Kelly mathematics, put some sort of investment into this expertise, and as a result, lose. Sooner or later. Okay, so that weight of correct and incorrect assumptions is very high for us. Let's then talk about assumption that football game or scoring in football game is actually a Poisson process. When when you read somewhere on the internet, you will find like hundreds and hundreds of different articles saying that football scoring football is a Poisson process, Poisson distribution. We find out this and that. This is the diagrams. And okay, so let's recall what the Poisson distribution is. So here is the sentence from Wikipedia, the definition, and constant mean rate, and independently on the same time since the last event. This is highlighted because it's really important to understand that you know that one event does not affect arrival of another event. It's like when you're waiting for buses at bus stop, you never know how many buses will arrive. Yeah, within an hour, for example. But you know that these buses will run independently on their route. Yeah? So one bus driver and one bus, second bus driver, second bus, and they drive, and some quantity of these buses will arrive within an hour. Would it be 0, 1, 2, 3, 4, 5? It is a kind of Poisson distribution. Maybe in average it would be 2, but it easily could be 0, yeah, if you're unlucky. And there is a diagram for Poisson. So if lambda, or mean expected number of events is 1, then it's like this. Maybe 4, this 10, it's like this. Okay, good. Nothing special here. What about football and Poisson distribution? Many sources from respected to, just randomly Googled are pointing that football scores can be approached with Poisson. Why Poisson? Because Poisson distribution implies very, very easy, great formulas to calculate every probability you're gonna have. Probability of winning, losing, draw, score difference, score sums, exact scores, both no scores, whatsoever. This can be calculated with formulas, so you only have to know these, these mean expected goals, yeah, and you can calculate everything. This is good. This is good. It must be Poisson, at least internet says so. Okay, Simon says, you repeat. Wikipedia says that World Cup soccer match has approximately 2.5 goals scored, and Poisson model is appropriate. Done. Very respected site 538.com says, our process of calculation constructed this way, so we take 2 Poisson distributions and turn them blah blah yada yada. Some easily Googled articles like Bookdown and sites like bookdown.org and beatthebookie.blog, they also say something. So we suspect that goal scoring in soccer modeled by Poisson process, Poisson distribution is widely used, and so on. By the way, this guy here, he or she has some doubts about it. But let's go further. So far, so good. Everyone says Poisson. Every site says Poisson. You are our valuable users. That you say, give us a Poisson calculator. No. Okay. It all starts, shattering with some minor problems. Okay. There is no problem in work published at Wikipedia, because maybe amount of games analyzed there was kind of small, maybe slightly over 1,000, of games in final rounds of World Cup, and statistics there cannot be trusted very, very, very much. So just approximately. If you look at diagrams of what you got in Poisson and what you got kind of in reality on each and every of that sites, you will find similarity. Like they look very similar. But sometimes, similarity can be deceiving, because you can, for example, say that the dog looks similar to the cat. Why not? If a dog of small size and cat of rather big size, they have same size, same amount of feet, legs, ears, eyes, whatsoever. But still, they are different and somehow treated as opposite, dogs and cats. So they look similar, but there are some minor problems. 538 reports, for example, that this approach they use leads to the effect that draw probability is undercounting. Something is wrong. So they have to do something manually afterwards. So they calculate that perfect probability, but then afterwards they have to do something manually with it. Inflate or deflate. Bookdown.org says, yes, we investigated, researched teams in Premier League, but for Liverpool, strange thing, it doesn't work, but it happens. No? BeatTheBookie.blog says, for lower average scores, it tends to underestimate low-scoring results, and then somewhere overestimate. Underestimation, overestimation, somewhere it is maybe 1% of probability. It's not that much, right? Still, yeah, you know. The problems are minor. Okay. But probably they are not just minor problems, because probably they show us to the fact it is not a Poisson. Right? To prove it or to check it, yeah, let's see how they construct the Poisson, how they treat it, and how they construct the goal scoring by Poisson. Everyone says Poisson process, and basically everyone means two different Poisson distributions. Okay? So, first of all, they say we calculate somehow average expected goals by team A, team B. This calculation is proprietary. So one calculates it one way, another calculates another way. Okay, calculate, done. Assume we know this. Point number 2. Step number 2, calculate probabilities of scoring. So we directly apply Poisson formula. And how do we know the probability of score? Right, we take probability that team A scored this score and probability of team B scored that score and multiply them, because they are independent. Okay. We heard it, we know this. Now let's check. Let's go to the data. We, every of those researchers respected, so we respect all of them, really, sincere respect. Still, every of them used some sort of restricted information, like let's focus only on English Premier League for certain seasons. Let's focus only on Soccer World Cup games, final rounds for all years, for example. Let's focus on these top 5 leagues, and so on. We will get access to much broader data than we use club games, and we will switch to it after our declaration of dependence. So actually, there you see calculate of probability of scoring is Poisson, and also this scoring is independent, so we can apply formula. We bust both points, so we say neither point 2 nor point 3 are correct, and there are dependencies. So what we say that independence of goal scoring of team. So it means that it is how much is scored by team A does not affect how much is scored by team B. We prove it is incorrect. Second is independence of future goals on past goals. It means, for example, in our examples, that independently on how much is scored in the first half, it does not affect the amount of goals scored in second half. Otherwise, it is not Poisson. Because, remember those bus drivers and buses, they are independent. It is independent on how many buses will arrive in minute 30 to 60. If you, for example, calculated how many buses arrived in minute 0 to minute 30. Okay? This is Poisson. And in football, it's not so. We use some data. It is what we use at our website, so it's whole UEFA zone, all 55 federations of it, Tier 1, Tier 2 leagues were applicable, the national cups were applicable, all major national cups, and also UEFA leagues, so Champions League, Europa League, and Conference League. Season starting 2011-2012 till now. We got some of over 300,000 games. And for them, we got scores, including scores in first half. Okay. Let's check it out. Oh, team scores. How scoring of home team affects scoring of away team. So we divided all games for the cases when home team scored 0 goals, and simply calculate average of away goals. It appears that away team scored like this, 1.42 goals in average. We admitted that if home team scored 1 goal at this game, then away team scored in average 1.28, a little bit less. If home team scores 2 goals, away team scores in average even less than that, so 1.19 of goals. And for 3 goals of home team, it would be 1.1 goals in average scored by away team in average. So the picture is that if home team scores more, the away team scores in average less. Same picture works in other directions. So that if away team scores 0, then it's 163. You may see that 163 is more than 142 because you have some home field advantage, right? If away team scores 1 goal and home team scores like this, a little bit less, and here a little bit less again, and less again. So if one team, so our hypothesis is they are dependent, and moreover we see this dependency right here and right now. If one team scores more, the other team scores less. So they have certain equilibrium, right? But yeah, if this equilibrium is not intact, then still, yeah. And of course, we did some mathematics called the chi-squared test of independence, or for independence, sorry. And it says home team scores, away team scores are dependent, so depend on each other. Great. This means, turning a few pages back, this means already we cannot use this formula. It is mathematically, theoretically, practically wrong. Okay. Let's go. Let's look at scores in first and second half. So again, we simply calculate how many goals scored in second half, depending on how many goals was scored in the first half. To calculate if they are probably dependent, and you see the more goals scored in the first half, the more goals are scored in second half. Right? There's a strict dependence. Chi-square test says dependent, everything says dependent. So number of goals in first half and number of goals in second half are dependent on each other. For us, that means that we cannot possibly say it is even Poisson. Even sum of goals is Poisson. It is not Poisson. There is a dependency. And it's okay for you if you kind of played football or kind of watched football. For you, it's an intuition, right? So that if probably there is a dry game, then okay, both teams know how to defend, and maybe they couldn't find ways how to score in the first half, but maybe the second half would be also not that full of goals. Or vice versa, if, for example, a stronger team plays with a weaker team, and stronger team finds keys to how to break up the bus of the weaker team 1-2 times, then maybe the second half would be also more goals. So it depends. It is dependent. The football is not the game. First of all, it's not the game where both teams play independently on each other. So it's not like team A goes and tries to score, and in parallel, somewhere in parallel universe, team B tries to make the score, and then you calculate this and say, okay, these two things are independent, and we use Poisson, for example, or we just multiply these probabilities, for instance, because they are not independent, they play independency. So if one game plays stronger, let's say, then probably it would concede less goals, not just score more goals, right? Same applies also to the scoring by itself. So that if you found a way how to score, then you learned from it, and probably there are motivations of team change. So one team wants to equalize, or you want to score more to secure the advantage or something, right? And once you smell the blood in the water, you might want to extend again the advantage, and then you score more. The probability of that you score, it increases, or the probability, the general probability that someone will score will increase. Yeah? And this makes our lovely football process not a Poisson process. Okay. If not Poisson, then what? Okay. If not Poisson, then what? It's a good question. If you learn mathematics or theory of probabilities, you might be knowing that the Poisson shape, that Poisson shape, does not belong solely to Poisson distributions. There are many other distributions, and as we discovered that the teams. So first we discovered that teams score dependently on each other. Then we must use something, not a combination of different distributions, but we must use some multinomial distributions depending on at least two random variables altogether, and solving dependencies between these variables somehow inside, right? And the second thing that we remember, that the more goals you score, the more goals, the probability that you score more, or everyone would score, it increases. Then it is like a biblical concept of the rich get richer and the poor get poorer, right? So that if you score, then you will probably score more. If you don't score, then you probably score even less. Yeah? Okay, and we found out that certain multinomial distribution, first, it's multinomial. Second, it complies with the concept rich get richer. Third, it approximates much better than Poisson distribution, in combination of Poisson distributions. it has formulas, and the greatest part of it, it can be visualized with some candies. So I hope that you can see 3 candies. One of them is white, one of them is green, one of them is red. Assume now that we have 3 teams playing. The reds play versus green. And Dirichlet-multinomial distribution says that it can be simulated with some good experiment. So we got a, let's say, small box with filled with different candies. The red candy means for us that red team scored 1 goal. The green candy means for us that green candy scored. And the white candy means that no team has scored. Okay? So we now play this experiment for 16 periods. For example, we divided football games into chunks of 6 minutes each. It's just for visualization. Normally must be something like 45 chunks or something like that, but to achieve better level of approximation. But this would be already instructive. And we put inside a lot of red and green candies. So that we put now it is there 80 candies overall, 10 red candies, 5 green candies, and 65 white candies. So that you may see the probability of not scoring is the greatest. Probability of scoring for reds is twice as more as probability of scoring for green. So let's play football. Reds versus green. And we say this approximation is better than what they say about Poisson. Okay, let's go. Yeah, so we take random. And it is white. Okay, so minute 6, no goals. Okay, teams are warming up. Something like that. The rule of Dirichlet-multinomial is simple. If you got white, if you got white, you're happy. And we are happy for you too. So we got second white and put it back. And minute 12. What is the outcome? Again, white. Okay, it's a dry game for now. So you can see that probability of not scoring is slowly increasing because there are more and more white candies over colored candies. Okay, minute 18. Let's see. Bad luck. But maybe there will be something, right? Okay. Go reds, go greens. Minute 24. Oh no, it was white, but something inside. You are substituted with 2 non-injured whites. Okay, minute 24:00. Minute 30, again white, so 0:0. Will we see the zeros after the final whistle? I don't know. Maybe. Let's try to pick some color. Yes! Reds scored. The strongest team now has a lead. So we now put 2 good reds inside. Minute 36:10. Minute 42. And we take white. Okay. Take white. We add some white. Minute 42. Let's go for... Oh no. Okay. There are some catastrophe is going on, right? So first half Oh, it doesn't look good. First half, 1-0 for the red. It's a bit hot, you know. I think in your country maybe too. So, the second half began with 1-0. So, minute, what kind of minute was 51? All right. We add some white. 0-1. Will the score remain until the game is finished? So let's do, minute 57. 0-1, 1-0. Reds are ahead. Okay, let's go. Minute 63, all the same. A bit boring, right? Okay, a lot of chocolate already on my hands. Minute 69. Bad hand. Minute 69. Okay, what is this? Minute 75. Adding whites. As you can imagine, the adding whites increase the probability of not scoring at all, even further. So 75, minute 81, no way, we must add white candy, yes. Minute 81, and now we go for something, let's go there, maybe. Minute 87, still 1-0 for the Reds. And the 9 minutes of the second half. Will there be something? Go Greens! Go Greens! Let's try this broken one. No! They failed to score. So, our experiment simulated the game ended with the small victory of Reds, 1-0. And we say that this approach with candies looks strange, but it is better for simulation than Poisson distribution. There, you must also find the average goals expected for Team A, for Team B, and a certain parameter which connects them all together in this game. So this is probability, for example, of not scoring a goal. Yeah. So you must find 3 probability and apply it together to get better probabilities. Still, we don't think it is the perfect approach. So it is better than Poisson. It is at least theoretically not incorrect comparing to Poisson when looking at data and understanding how the football is going on, right? But still it's not perfect. We found out that behavior of this rich get richer can vary from home team and away team, so they have different motivations of scoring or not scoring. And for example, if score is 1, becomes, for example, sometimes 2-1, then it is important. Was it before 1-1 and became 2-1, or it was 2-0 and became 2-1? Yeah, because then things change. We still could not find the good answer. What and how can football be simulated? But at least we found something better and something more natively clear than Poisson distribution. And again, if you use wrong assumptions, this leads you basically nowhere. Use correct assumptions. Our assumption is that we don't know what the distribution of football goal scores. It is a bit dissatisfying, I know that. Still, it leads us to the outcome that probably we should use means of statistics, of machine learning, of artificial intelligence. Because, machine learning and artificial intelligence are used exactly where you cannot scientifically say, what am I dealing with? And we cannot say what we are dealing with. We only try to approach, and we found a bit closer approach to it. Hey, I hope you guys will do good assumptions after it. And I hope you guys had fun and it was also useful for you. If you have any questions about data and what we did and so on, let us know in comments. And generally, comment, criticize, ask, like, dislike, share, subscribe. We're always glad to talk to you. Thank you. Stay with us. Bye-bye.